Welcome to AI Frontiers, a podcast that explores the cutting edge of machine learning research. In today's episode, Breaking Boundaries, ML's Next Frontier, we'll be synthesizing research papers from May 19, 2025. This podcast aims to provide you with a comprehensive analysis of the latest advances in machine learning research across diverse topics. We'll examine groundbreaking findings, methodological innovations, and emerging trends that are shaping the future of artificial intelligence. By the end of this episode, you'll have a clear understanding of where machine learning research stands today and the exciting directions it's headed. Let's dive into the fascinating world of AI's next frontier, where researchers are pushing boundaries and redefining what's possible with machine learning technology. Let's begin with an overview of today's presentation. We'll be exploring the cutting edge of machine learning, tracing its remarkable evolution from a primarily academic pursuit to one of the most transformative technologies of our time. Our discussion will cover 6 key research themes that define today's innovation landscape, from efficiency enhancements in large language models to novel approaches in physics-informed machine learning. We'll examine groundbreaking findings that are reshaping our understanding of AI capabilities, including significant advances in one-step generative models and non-invasive brain-computer interfaces. Throughout the episode, we'll analyze the methodological approaches driving progress across domains, highlighting both their strengths and limitations. Finally, we'll discuss future directions and implications for the field, providing insight into where machine learning research is headed in the coming years. Before diving into specific research themes, let's establish a clear understanding of where machine learning stands today. Machine learning has undergone a remarkable transformation, evolving from a niche research area to a transformative technology that powers countless applications in our daily lives. From recommendation systems that personalize our online experiences to sophisticated medical diagnostic tools that identify diseases from medical images, machine learning has become ubiquitous across sectors. Current research addresses several fundamental challenges, including improving computational efficiency, enhancing model interpretability, ensuring fairness across diverse populations, and building robust systems that perform reliably in dynamic environments. What makes this moment in machine learning particularly exciting is the rapid pace of innovation occurring simultaneously across multiple fronts. Researchers are exploring diverse approaches, including supervised learning with labeled data, unsupervised learning that identifies patterns without explicit guidance, and reinforcement learning where agents learn through environmental interaction. The first major research theme we observe in recent publications is the ongoing effort to enhance the efficiency of large language models. As these models grow in size and capability, their computational requirements have become increasingly challenging, particularly for deployment in resource-constrained environments. Several innovative approaches have emerged to address this challenge. Deng and colleagues introduced multi-head temporal latent attention, a technique that dynamically merges temporally adjacent key-value cache vectors in transformer models. This method achieved remarkable results, reducing memory usage by 8.3 times while maintaining translation quality in English-German speech translation experiments. Another significant innovation is fractured chain-of-thought reasoning, which strategically truncates reasoning paths to dramatically reduce token consumption in large language models. This research challenges the conventional assumption that exhaustive step-by-step reasoning is necessary for optimal performance. The findings demonstrate that partial reasoning, when properly managed, can be just as effective as complete reasoning traces. These memory optimization techniques, particularly those focusing on compressing key-value caches, make advanced AI capabilities more accessible in settings with limited computational resources. The second research theme focuses on domain generalization, developing models that perform well across diverse and dynamic environments, even when trained primarily on data from a single source. As machine learning systems are deployed in increasingly varied settings, this capability has become essential for real-world applications. Parameter-Space Ensemble with Entropy Regularization represents a notable advance in this area, specifically addressing the performance fluctuation often observed in augmentation-based domain generalization approaches. This method employs a proxy model to learn from augmented data on behalf of the main model, progressively accumulating knowledge through parameter averaging. Another innovative approach called FreKoo analyzes parameter trajectories in the frequency domain to disentangle evolution patterns in temporal data. By applying Fourier transforms to model parameters, this technique separates long-term structure captured in low-frequency components from local uncertainties represented by high-frequency components. This multi-scale approach has demonstrated significant advantages over existing temporal domain generalization methods, particularly in streaming scenarios with complex drifts and uncertainties. The third research theme represents a growing integration of scientific principles with data-driven approaches, physics-informed machine learning. This hybrid approach leverages both the pattern recognition capabilities of neural networks and established scientific understanding, creating models that respect fundamental physical laws. The PhyDA framework exemplifies this approach by incorporating atmospheric science constraints into diffusion models. By ensuring generated outputs obey relevant physical laws, this method produces more accurate and physically plausible reconstructions of atmospheric states from sparse observations. Another significant contribution comes from the AdS-GNN, a graph neural network that respects conformal symmetries, transformations that preserve angles, by lifting data to anti-de Sitter space. This mathematical approach ensures the network inherently respects important physical principles, improving generalization in tasks ranging from computer vision to statistical physics. These hybrid methods demonstrate how domain knowledge can be effectively combined with data-driven learning to create more robust and scientifically consistent models, particularly valuable in scientific applications where physical constraints must be satisfied. The fourth research theme centers on enhancing reasoning capabilities in large language models. While these models have demonstrated impressive performance across various tasks, improving their ability to perform complex reasoning remains an active area of research with significant practical implications. Latent represents an innovative approach to this challenge, enhancing language model reasoning through test-time instance-level adaptation within the model's latent space. Unlike prior methods focused on token space, this approach leverages policy gradient to iteratively update latent representations guided by self-generated reward signals. The method consistently outperforms strong baselines, including chain-of-thought prompting and fine-tuning-based approaches, across multiple reasoning benchmarks and model architectures. Another significant contribution is the CERT framework, which manages reasoning to be short and right by dynamically pruning low-quality reasoning branches. This approach not only improves reasoning accuracy but also substantially enhances serving efficiency, achieving improvements of up to 28.2 times while maintaining comparable accuracy. These advances demonstrate how targeted optimization of reasoning processes can yield both performance and efficiency gains in large language models. Across the research papers we've analyzed, several groundbreaking findings stand out for their potential to reshape the field. Mean flow represents a significant advance in efficient generative models, achieving an FID score of 3.43 with just a single function evaluation on ImageNet 256 by 256 trained from scratch. This substantially narrows the gap between one-step models and their multi-step counterparts, potentially enabling real-time high-quality image generation for applications where computational efficiency is crucial. Another remarkable breakthrough comes from the first non-invasive brain-to-text system that significantly exceeds critical baselines, raising BLEU scores by 1.4 to 2.6 times over prior work. This achievement eliminates the need for surgical implants, potentially making brain-computer interface technology accessible to a much wider population. In the domain of model routing, research has shown that simple k-nearest neighbors approaches often outperform complex learned routers for large language models, challenging conventional wisdom about routing complexity. Additionally, a multi-layer memristor architecture has achieved superlinear capacity scaling proportional to n to the power of 1.74, fundamentally challenging our understanding of associative memory capacity limits. Finally, Ultra-Delta has demonstrated unprecedented compression of fine-tuned models, reducing Llama 2 model size by up to 133 times while maintaining performance. Looking across the research landscape, several methodological approaches appear consistently, driving innovation across different domains. Diffusion models have emerged as a powerful generative approach, progressively adding noise to data and then learning to reverse this process. Their strength lies in generating high-quality, diverse samples that capture complex data distributions, and they can be effectively combined with physical constraints to ensure outputs satisfy specific properties. Attention mechanisms, particularly as implemented in transformer architectures, continue to play a central role in capturing long-range dependencies in sequential data. Recent work has focused on optimizing these mechanisms for greater efficiency. Reinforcement learning enables agents to learn optimal behaviors through environmental interaction, though researchers continue to address challenges related to sample efficiency and reward design. Federated learning preserves privacy by enabling model training across decentralized devices without exchanging raw data, with recent advances focusing on handling data heterogeneity. Finally, knowledge distillation techniques compress large models while maintaining performance, making advanced capabilities available in resource-constrained settings. Let's examine one seminal paper in greater detail. Multi-head temporal latent attention, by Deng and colleagues from 2025. This work addresses one of the most significant bottlenecks in transformer architectures: the memory requirements of the key-value cache during inference. While transformer self-attention has enabled breakthroughs across numerous domains, the key-value cache grows linearly with sequence length, limiting practical applications for long-sequence tasks such as speech processing and document summarization. The authors introduce a hyper-network approach to dynamically merge temporally adjacent key-value cache vectors, significantly reducing memory footprint while maintaining performance. A key innovation is their stride-aware causal mask, which addresses the mismatch between compressed key-value cache and processed sequence lengths. This mask ensures efficient parallel training and consistency with inference behavior, enabling the model to learn appropriate temporal compression strategies. In speech translation experiments, this method achieved a 5.3 times speedup and reduced GPU memory usage by a factor of 8.3 while maintaining translation quality. This paper was selected for discussion due to its transformative potential for long-sequence transformer applications, addressing a fundamental limitation of these powerful architectures. The second seminal paper we'll examine focuses on non-invasive brain-to-text systems, representing a groundbreaking advance in assistive technology. This research reports the first non-invasive brain-to-text result that significantly exceeds critical baselines, raising BLEU scores by 1.4 to 2.6 times over prior work. What makes this achievement particularly significant is that it eliminates the need for surgical implants, potentially making brain-computer interface technology accessible to a much wider population, including those with severe motor disabilities. The researchers achieved this breakthrough through three key innovations: extending word classification models with large language model-based rescoring to improve accuracy, introducing a predictive infilling approach to handle out-of-vocabulary words, and demonstrating how to scale non-invasive brain-to-text models across datasets. This work removes a major obstacle to practical non-invasive brain-to-text systems and could revolutionize assistive technologies for people with communication difficulties. The implications extend beyond assistive technology, potentially opening new avenues for human-computer interaction that could benefit broader populations. The third seminal paper we'll examine introduces sinusoidal initialization, fundamentally challenging the orthodoxy of random initialization in neural networks. This groundbreaking research introduces a deterministic initialization method based on sinusoidal functions, constructing structured weight matrices with evenly distributed values. The approach leads to more balanced neuron activations from the first forward pass, in contrast to the potentially uneven activation patterns that can result from random initialization. Across a wide range of model architectures, including convolutional neural networks, vision transformers, and large language models, sinusoidal initialization consistently delivered faster convergence, greater training stability, and higher final accuracy compared to standard random initialization methods. This paper was selected for discussion because it challenges one of the most fundamental assumptions in neural network training: that random initialization is optimal. By demonstrating that a carefully designed deterministic approach can outperform randomness, this research opens new avenues for understanding neural network optimization and may lead to significant improvements in training efficiency and model performance across diverse applications. Looking toward the future, several clear directions emerge for machine learning research. First, we anticipate continued focus on efficiency optimizations that enable deployment of advanced models in resource-constrained environments. As AI applications expand to edge devices, mobile platforms, and regions with limited computational infrastructure, techniques that reduce memory, computation, and energy requirements will become increasingly valuable. Second, the integration of physical principles into learning algorithms is likely to accelerate across scientific domains, from climate science to materials discovery. These physics-informed approaches promise more accurate, reliable, and interpretable models for scientific applications. Third, improved reasoning capabilities through novel latent space optimization techniques will continue to be a priority, enhancing the ability of large language models to perform complex logical and mathematical reasoning. Fourth, as machine learning systems become more widely deployed, advanced security and privacy-preserving methods will be essential for robust implementation in sensitive domains. Finally, we expect to see continued exploration of novel initialization and training strategies that challenge conventional wisdom, potentially leading to fundamental improvements in how neural networks are designed and optimized. It's worth noting how this presentation itself was created, as it represents an example of AI synthesis and review in action. The content for this podcast was synthesized using GPT and Anthropic's Claude 3-7 Sonnet 20250219, advanced language models capable of analyzing and summarizing technical research. Voice narration was generated using DeepGram's TTS synthesis technology, converting the text into natural-sounding speech. The visual elements for the accompanying slides were created using Grok image generation capabilities, producing informative graphics that complement the narration. While this process leveraged advanced AI tools, all content underwent human expert review to ensure accuracy and coherence. This combination of AI synthesis and human oversight represents an emerging approach to content creation that can efficiently process large volumes of technical information while maintaining quality standards. While comprehensive, we acknowledge that some oversights may exist in our analysis. Detailed references to the original research papers are provided for listeners interested in exploring any topic in greater depth. Subscribe to AI Frontiers to stay updated on cutting-edge research in artificial intelligence and machine learning. Our YouTube channel offers weekly research syntheses covering the latest breakthroughs across the AI landscape. Each episode provides comprehensive coverage of emerging technologies, methodologies, and applications, delivered with expert analysis and accessible explanations of complex concepts. Join our growing community of AI enthusiasts and researchers to stay informed about developments shaping the future of technology. No website needed. Find all our content directly on YouTube. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer. This video uses archive.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by archive.org.